Okay, welcome back. Today, we're going to look at section 6.5, which is on applications of exponents and logarithms. Most notably, we're going to talk about interest, simple, and compounds today, and then we're going to take a little bit of a look at growth and decay exponentially. We'll start off with interest, and so we'll start off with the most basic type of interest, which is simple interest. So the idea is that let's say that you invest $100 at 5% annual interest. So we can kind of make a table of values for, let's say, T in years and A in dollars being the amount of money that you'll have. In year 0, you'll have $100. After 1 year, 105. 2 years, 110, 115, and so on. 5% of 100 is $5. So at the end of each year, you'll get an additional $5. This is the idea of simple interest. And the formula is that the amount of interest is equal to the initial amount of money, called the principal, multiplied the interest rate, multiplied by the time. So the interest is equal to the principal, or initial amount of money, multiplied by the annual rate, multiplied by the number of years. This means that the final amount, which is going to be equal to the principal plus the interest, will be equal to P plus PRT, or factoring out the P times 1 plus RT. We can use this idea to calculate how much simple interest we will owe or acquire after a certain amount of time, and also to determine how much the final amount will be. Now, simple interest is really easy to find, but it doesn't do a good job of showing what goes on in the real world, because when you make an investment, it doesn't work like this. The $100 that we put in at the start, yes, 5% of that was $5. But after a year, we had $105. That should have been earning interest, not the original 100. So the 5% should have been a little bit larger. It should have ended up being $5.25. So we should have gotten a little bit more the next year and a little bit more the year after. As a result, we're going to need a more complicated formula, and the idea is called compound interest. And the idea of compound interest is that the interest earns interest. So let's take the same scenario. And let's say that at year 0, you've still got $100, and at year 1, you've got 105. Because 5% of 100 is 5. So we added that in. But now 5% of 105 is 105 and 25 cents. So that means that after 2 years, we'll have 110.25. After 3 years, we'll need to find 5% of that again. And this is where we'll probably start needing a calculator. So 110.25 times 0.05 comes out to be 5% of 110.25 is 5.5125. So rounded to the nearest penny, after 3 years, we're going to have 115.76. And always we're going up a little bit more than we did the previous time. Now, this interest compounding is what ends up making a difference. After 3 years of compounding this interest, we're up about 76 cents of what we would have been over simple interest. So it's not a huge deal in this case, but it ends up being significant. And the formula here is that each time you're simply multiplying by the new percentage. So since you're multiplying repeatedly by the interest percentage, that shows up as an exponent. The formula is P times 1 plus R to the T. This is for annual compound interest. However, this begs a really important question. Why is the interest compounded at the end of the year? Is that fair? Usually when you invest in money, it's not invested for entire years. You might invest it for multiple years or for shorter periods of time. If I put my money in the bank for only a month, do I get nothing? That doesn't seem very fair. What if I put it in for 11 months? Then getting nothing seems extraordinarily unfair. So should they compound halfway through the year instead? Well, then why wouldn't I just take it out after 6 months and get an entire year's bonus? Then just put it right back in. That wouldn't be very fair to the banks. So what most banks do is they compound the interest multiple times per year, only the part of the interest that should have been earned. So for example, compound monthly means that 12 times per year, the bank will compound the interest. Let's go ahead over to a Google Doc so that we can take a look at what this looks like in the long term. So we'll go ahead. I'm going over to Google Docs because I don't have Excel on this computer, but I want to be able to use Excel. So let's switch ourselves over here. Okay, so let's take the same basic idea. So we'll let this column be the number of years. We'll say this one is compound annually. And then we'll make a couple of other columns. Let's say this one is compound 2 times per year, which would happen. We will say compound 4 times per year. And then we will say compound 12 times per year. And there's terms for each of these. So twice a year will end up being semi-annually. 4 times a year, we would say quarterly. And 12 times a year, we would say monthly. So let's then make a new column for months. So when t is equal to 0, at the start of each of these, we will have $100. And 0 months will have gone by. And then we'll look at the amount that happens after each of these amount of months. And let's take a look over the first 3 years. So we'll go up to 36 months. At the end of 12 months, t will be 1, 2, and 3. So for the compound annually, the idea is that it will stay as $100 for the first 11 months, and then at 12 months, it will multiply by the interest rate. So we will be equal to the initial amount times 1.05, because the original amount adds 5% interest. And then we will stick with that amount until here. Oh, come on. This should just stay at 105. Whatever. 105. Until it gets to here, in which case it will equal the previous 105 multiplied again by 1.05. And it will stay this way until 3 years have gone by, in which case it will again multiply by 1.05. However, when we compound for different amounts of time, this will change. So this was compounded annually. Next, we wanted to look at compound twice per year, which was semi-annually. And so this time, the $100 will stay the same for the first 5 months. But when I reach the 6th month, we will take the original amount and multiply, not by 1.05, because that would be a whole year's interest, but by 1.025, which is half a year's interest. And this amount will stay the same until we reach 12 months, at which point we will multiply by the previous month again times 1.025. Let's see if this will work. Not quite. So I will take this and put it here. Does that work? Nice. So we can copy this pattern down each time, multiplying by the new interest that we should have. And we see that at the end, we end up with slightly more money than we did originally. We can repeat this process for compound 4 times per year, which is monthly, which means that it will stay the same for 2 months, and then it will multiply the original amount by 0.05 over 4 is the amount of interest rate that we should have. And we can take this interest and copy it so that every 3 months we get this new amount of interest. And we see that the more frequently you compound, the more money you have. It's not a huge difference, but it does make a difference. If we take compound monthly, then every single month, we will take the previous amount of money and multiply by 1 plus 0.05 divided by 12. And we can just take this and bring the pattern down. And we see that we end up with a little bit more money. I want to add in one more column, which would just be simple interest, which means simply every year we take the original amount and add $5. So compare these amounts of money with simple interest as opposed to compounding annually, twice a year, 4 times a year, or 12 times a year. The more times we compound, the more money we end up getting. Now, it's not a massive difference. The difference between $115 and $116.14. 12 compounds per year over 3 years only nets us an extra $1.15 or so. So it's not a huge amount of money, but it's nice because it frequently updates how much there should be, and it does give a little bit more. The formula for compounding multiple times per year is going to end up being P times 1 plus R over N to the N times T, where N is the number of compounds per year. Let's do one example with this. Suppose that we invest 500 in an account with a 0.75% interest rate compounded monthly. We want to figure out how much money will be in the account after 5 years and how long it will take for the investment to double. So we will be using the P times 1 plus R over N to the NT formula. We can fill in some amounts that will be the same. The initial investment was $500. The interest rate is 0.0075. Remember, since it's given as a percent, we'll want to change it to a decimal. And the number of times compounded is 12. Thus, we'll just have to figure out for each piece what we know and what we don't. For the first one, I want to know how much money will be in the account after 5 years. So A will be 500 times 1 plus 0.0075 over 12 to the 12 times 5. This is surely a job for our calculator, so I'll pull one up for myself and plug it in. So 500 times 1 plus 0.0075 divided by 12 to the 12 times 5. I am getting out for myself $519 and about 10 cents. For the second one, it's asking how long it will take the initial investment to double. So this time, the final amount would be $1,000. And this time we're trying to solve for the exponent. Now I'm going to give us a little bit more space here because since we're solving an equation where we're not trying to isolate the exponent, we know that we'll need to use the methods we learned last time. Isolate the exponent, use a log to cancel, and then solve. Here, this will give us, we will first divide both sides by 500. 2 is equal to this exponential piece. Next, we'll go ahead and cancel. I don't want to use a log of this big ugly base. I'm just going to use an ln, let's say. Which will get us 12t is equal to ln of 2 divided by ln of this big chunk. Thus, t is equal to all of this over 12. Again, we can plug this much into a calculator. And so let's see. ln of 2 divided by ln 1 plus 0.0075 over 12 divided by 12. And I am getting 92 years. So we can answer each of these questions. How much money will be in the account after 5 years? We will have about 519.10, and it will take 92 years for a $500 investment to double at only 0.75% interest. Now, let's consider a very simple example here because I want to show something very interesting off. Consider the fact that $1 is invested at 100% interest for 1 year. And what I want to do is similar to last time, figure out how much we will have based on different amounts of compound. I'm going to bring us back over to a Google Doc for a moment. And let's take a look at the different options. So what I'm going to do is I'm going to consider the amount of money based on different values of n. So n is going to be the number of times that we compound per year. So we'll start off with n being small, 1 and 2. With the amount of money is going to be equal to, we had a $1 investment. We had a 100% interest rate, so it'd be 1 over n, which is this number, to the power of n. For Google Docs, the caret key I don't think does powers for us, so we're going to have to use, instead of a caret, we're going to have to do a different argument, which is the power function, where we will first put in the base and then the exponent. So the base is 1 plus 1 divided by this number, and the power is this number times 1 for 1 year. So we see that if I'm just compounded once, then I will end up with $2. That makes sense. 100% interest on $1 would give me $2. If I compound twice per year, then I end up with $2.25, a little bit extra. First, let's just take a look at some of the other common values. We said 4 times a year was a common one for quarterly, and then 12 would be monthly. So we see that we're getting more money. $2, $2.25, up to monthly is about $2.61. So this gives me an idea. Well, compounding very frequently is making me more money. So why don't I just take my money out of the bank and put it back in really frequently? If I keep taking it out and putting it back in, they'll have to compound it more quickly in order to be fair. And that should just get me way more money. This is a nice get rich quick scheme that I might be able to use, where I sit in front of the bank, they compound my money, and I get money for doing nothing. So let's suppose that I every single week go to the bank, take my money out, and put it back in. Well, I will end up with $2.69. That's an extra 8 cents over doing it once per month. Okay, maybe I wasn't doing it enough. I'll go every single day. I got an extra 2 cents. Okay, well, this is starting to seem like it's going to be a bit of a hassle. Okay, let's suppose that I go 1,000,000 times every single year. I made an extra 4/10 of a cent. That sounds not very worth it. And so you can see the idea of what's happening here. Number one, compounding more certainly gets us more money, but the amount extra that it gets doesn't actually end up making that big of a difference. When we increase by a very large amount of compounds, the amount of money doesn't go up that much after the initial chunk. The first 12 put us up from $2 to $2.61, so that made a difference. But the next million only put us up 10 more cents. So the first increases were important. And second of all, take a look at this final number, 2.71. Does that sound familiar? That's E. This right here is why we care so much about E, is because if you take these investments and you compound them continuously, so not 1,000,000 times, but you are always compounding. Any amount of interest that you earn is immediately applied and immediately starts earning more interest. That is where E comes into play. And so bringing us back here, we will say that we have this new formula based on this E, where the amount of money is equal to the principal times E to the RT. This is the formula for compounded continuously. And we will use this when discussing compounded continuously. And this right here is one of the many, many reasons why E is so important. To summarize what we had on the Excel document, we were saying that if we considered 1 times 1 plus 1 over n to the power of n, which is the formula that we were using, as n gets very large, in other words, as n approaches infinity, let's say that this was equal to our amount, the amount approaches E. This is a graph with an asymptote of E. Starting at 2 and ending at E. That is why we care about E. Now, with all that in mind, let's shift gears and move on to growth and decay. Because this is going to be something else, and we'll see that E is coming into play again. I'm not going to go through as in-depth an example of why we care about E, but just keep in mind that E ends up being an important number here. So if a quantity is growing or decaying proportionally to its size, then we will be using an exponential formula to track this change. The formula here is given by Q of t is equal to Q0 times e to the kt. Q0 will be the initial quantity, and k we'll call the constant of proportionality, where a larger k indicates that we're growing, whereas a smaller k indicates that we're decaying. A couple of examples where this could come into play would be investment, like we saw before. Investment of money compounded continuously has exponential growth. We have the idea of population growth. The more people there are, or bunnies, or cells in a petri dish, the faster the population will grow. You could have the idea of radioactive decay, where something has a half-life, and the more of it there is, the more quickly it decays. But as it starts to decay, there becomes less of it, so it decays more slowly. You could have the idea of something cooling off or heating up inside of a room, heating up or cooling off and approaching a given temperature, like we saw in the previous example in an earlier video with a cup of coffee. Let's just go through one example here of setting up and working with an equation. So the half-life of a radioactive isotope is the amount of time it takes for half of the radioactive material to decay. Cobalt-60 has a half-life of 5.27 years. So you would like to find an equation representing the amount of 50 grams of a sample after t years. So there's two approaches for this. I'm going to show you both. The first one is that we will use the setup. Q is equal to Q0 times e to the kt. And we'll plug in what we know. Number one, Q0 is equal to 50. Number two, after 5.27 years, half of that would be remaining. So 25 would be 50 times e to the k times 5.27. That means that 1/2 is e to the k times 5.27, which means that 5.27k is equal to ln of 1/2, which we get by taking the ln of both sides and canceling out the e, which means that k is equal to ln of 1/2 divided by 5.27. We'll have to plug that into our calculator, of course. So if we plug that in, ln of 0.5 is about 0.69 negative, and divide by 5.27 gives us negative 0.132. So the equation is Q is equal to 50 e to the negative 0.132 times t, where t is in years. The other way we can do this is, instead of using the basic form, thinking about this as a 1/2. we'll still have 50, but instead we will use 1/2 as our base. We know that every time t increases by 5.27, then I need to multiply by 1/2. So using 1/2 as a base makes a lot of sense. We will end up using t divided by 5.27. That way, when t equals 27, it cancels out and our exponent is 1, leaving us with 25. Either of these two methods will end up working, and you are welcome to use either. That's all we've got for this one. We'll see you guys next chapter.